Hi, welcome back. Today we're going to start function operations. What we're actually doing is something called compositions of functions. Compositions of functions is where you're given two functions and you're expected to insert one of the functions into the other one. And so depending on the order in which it's given, you'll see how that actually works. The official definition is an operation which uses the output from one function as the input of a second function. So we're basically taking a y value and plugging it in as an x value of a second function. So we're going to start with each of the four properties, addition, subtraction, multiplication, and division of functions, and we'll look at how each of those works using a specific example and then generally using just x. So using plus, you'll notice the notation here actually means this plus that. So in this case, I'm going to take my -6, I'm going to plug it in for every x value that I see in each of the two equations, and then add those numbers together. So it looks like this. I'm going to simplify my numbers, and finally the answer is 47. Keeping it generally with just the variable x looks like this. Combine like terms. Compositions of functions is not extremely difficult. You just have to pay attention to each of the symbols that you're using. We're going to have to refer back up to the top of the page for each one of these problems, so just remember we're always using 3x minus 5 and 4x regardless of which example we're working on. This time we're going to use subtraction, but the process is still going to be the same. Substitute 4 for x, and instead of adding, subtract. In general terms, combine like terms, and number 3. Multiplication, I'm going to use parentheses rather than an x or a dot, just kind of helps separate it a little bit easier. So using the specific example of 8, remember we're substituting 8 for every value of x in each one of the equations. I'm going to employ the distributive property here to get that to work. Simplified expression looks like that. Remember, when you're dealing with compositions of functions using division, you're going to want to use your restriction. We'll get to that in just a second. Remember, the restriction is when the denominator is equal to 0. That does not apply when we're using a number example like this one, but it will apply to letter B. Okay, in this one, we're going to do 3x minus 5, and typically you will not see a lot of simplification here, but just remember you have a domain restriction, and that particular domain restriction is when x is equal to 0. Alright, we're going to take a look at a few more examples so that you can see how this works in other formats as well. Remember, f of x is a variable. The f of x portion actually stands for y, and the value inside the parentheses stands for x. So in this particular example, we are going to substitute x for 4, and we are going to do that in the f function, not the g function. So you have to be a little bit observant so you know which one you're actually using. So that means I'm going to substitute and get 4 squared, which is 16. Again, I'm going to substitute x and to the f function, and I get -2 squared. Contrary to what your calculator thinks, that is actually a positive value, 4. We'll talk more about that, but remember, a negative times a negative is always a positive. Now we're switching gears. We're at the g function now. We're still substituting for x, so it looks like this. And the square root of 4 is 2. Down to example D. Alright, we're doing the exact same thing, except this time we're substituting a negative number into the radical, which gives us a negative radicand. Now it becomes an issue because this is an undefined value. So we're going to go ahead and stop here for now. When we get into the quadratics unit, you will learn of something called an imaginary number. So this is an imaginary solution, and we will leave it at that at this point. Later on we will discuss this and talk more about what imaginary solutions look like and how we actually solve them. Back into our operations here, we're going to go ahead and add these two together. So it's going to be x squared plus the square root of x plus 1. Nothing to combine here because I have no like terms, so this is my final simplified form. Likewise, x squared x plus 1. Nothing to combine here. Likewise, x squared times the square root of x plus 1. Nothing to combine here, so I'm finished. And now I have x squared divided by the square root of x plus 1. Now remember what I said, when we use the compositions of functions and division, we've got to include the restriction. In this case, we have both restrictions at the same time, and the value that the denominator cannot be equal to is -1. At the same time, it must be greater than or equal to -1 to keep this radicand a positive number. Therefore, the restriction on this particular problem is x must be greater than -1. Alright, back to the top up here. We're going to go ahead and take a look at these two problems. And then I'm going to leave these last two SAT challenge problems for you. We're going to have a class discussion about them tomorrow to make sure that you guys are actually working these problems and getting prepared for your PSAT, which is coming up very soon. Alright, multiplication. X squared times x squared. Properties of exponents tell me to add. Gives me x to the 4th power. G of f of x means that I'm going to insert the f of x function into the x value of the g function. So the g function is the square root of x plus 1. I'm going to substitute the f function, which is x squared, into that x values. And that is my composition of functions. Please take a look at these two problems. Work through them based on what you know of compositions of functions, and see if you can get the solution to them both. Tomorrow we'll have a class discussion during our warm-up to determine how you found your answers, what ways you found your solutions, so we can decide on what SAT strategies are being used in these two particular functions, or two particular problems.